Hello everyone, and welcome back to the introductory module on properties of solutions. It should not be surprising for you to learn that some physical properties of solutions differ in important ways from those of the pure solvent. For example, pure water freezes at 0 degrees, but aqueous solutions freeze at lower temperatures. We apply this principle when we add ethylene glycol antifreeze to a car's radiator to lower the freezing point of the solution. The added solute also raises the boiling point of the solution above that of pure water, making it possible to operate the engine at a higher temperature. Lowering the freezing point and raising the boiling point are physical properties of solutions that depend on the concentration, but not on the type or identity of the solute particles. Another interesting phenomenon can be observed if you scatter a small amount of icing sugar on a bowl of strawberries. If you do so, you will find that the strawberries appear to become juicier. In fact, the sugar draws juice from inside the cells of the fruit to the outside. This process is called osmosis and, along with freezing point depression and boiling point elevation, is known as a colligative property, which will be the main topic of this lecture. In a previous lecture, you learned that a liquid exerts a characteristic vapor pressure, which is the pressure of a vapor in thermodynamic equilibrium with its condensed phases in a closed container. When a non-volatile solute is dissolved in a liquid, the vapor pressure exerted by the liquid decreases. The difference between the vapor pressure of a pure solvent and that of the corresponding solution depends on the concentration of the solute in the solution. This relationship is expressed by Raoult's law, which states that the decrease in vapor pressure is directly proportional to the solute concentration, expressed as a mole fraction. To understand the phenomenon of vapor pressure lowering, we must consider the degree of order in the states of matter involved. Molecules in the liquid state are relatively ordered, meaning they have low entropy, while molecules in the gas phase are much less ordered and have high entropy. Since there is a natural tendency toward increased entropy, molecules tend to move from regions of lower entropy to those of higher entropy. This results in molecules leaving the liquid and entering the gas phase. As you have seen, when a solute is added to a liquid, the molecules of the solvent are pushed away from each other, disrupting the liquid's order. As a result, the solution has greater entropy than the pure liquid. Because the difference in entropy between the solution and the gas phase is smaller than that between the pure liquid and the gas phase, there's a decreased tendency for molecules to leave the solution and enter the gas phase, resulting in a lower vapor pressure exerted by the solvent. This qualitative explanation of vapor pressure lowering can be illustrated by the following figure. To summarize, the smaller difference in entropy between the solution and gas phases compared to that between the pure liquid and gas phases, results in a decreased tendency for solvent molecules to enter the gas phase, leading to a lowering of vapor pressure. Just keep in mind that the solvent in a solution will always exert a lower vapor pressure than the pure solvent. I hope you know that the boiling point of substance is the temperature at which its vapor pressure equals the external atmospheric pressure. Since the presence of a non-volatile solute lowers the vapor pressure of a solution, it also raises the boiling point of the solution relative to that of the pure solvent. At any given temperature, the vapor pressure over a solution is lower than that over the pure liquid. Consequently, a higher temperature is required to make the solvent's vapor pressure equal to atmospheric pressure compared to the pure solvent. Hence, solutions always have higher boiling points than pure solvents. The value of the boiling point elevation is proportional to the concentration of the solute in the solution, expressed in molality. This relationship is represented by the equation shown on the right, where m is the molality of the solution and Kb is the mole boiling point elevation constant. Now let's see what happens to the freezing point of solutions. If you have ever lived in a cold climate, you may have seen roads and sidewalks salted during winter. Applying a salt such as sodium chloride or calcium chloride thaws ice or prevents its formation by lowering the freezing point of water. The freezing point depression in solutions is directly proportional to the molar concentration of the solution. This relationship is represented by the equation shown here, where m is the concentration of the solute expressed in molality, and Kf is the molar freezing point depression constant. Like boiling point elevation, freezing point depression can be explained in terms of differences in entropy or disorder. Freezing involves a transition from the more disordered liquid state to the more ordered solid state. For this to happen, energy must be removed from the system. Since a solution has greater disorder than the solvent, there is a larger difference in entropy between the solution and the solid than between the pure solvent and the solid. This larger difference in entropy means that more energy must be removed for the liquid-solid transition to occur. In other words, the solution freezes at a lower temperature than the pure solvent. Also note that boiling point elevation occurs only when the solute is non-volatile, whereas freezing point depression occurs regardless of the solute's volatility, as vapor pressure plays no role in freezing. In the end, we should briefly discuss perhaps the most important colligative property for biomedical students: osmotic pressure. Many chemical and biological processes depend on osmosis, which is the selective passage of solvent molecules through a porous membrane from a more dilute solution to a more concentrated one. The figure here is one of the best illustrations of osmosis. The left compartment of the apparatus contains pure solvent, while the right compartment contains a solution made with the same solvent. The two compartments are separated by a semi-permeable membrane, which allows the passage of solvent molecules but blocks the passage of dissolved particles. Initially, the liquid levels in the two tubes are equal. However, as time passes, the level in the right tube rises, continuing to do so until equilibrium is reached, at which point no further net change in levels is observed. The osmotic pressure of a solution is the pressure required to stop osmosis. As shown in the figure on the right, this pressure can be measured directly from the difference in the final liquid levels. At this point, you might rightfully ask, what causes water to move spontaneously from left to right in this apparatus? Well, to understand the driving force behind osmosis, we should look at another situation depicted in this figure, where we have a container of pure solvent and a solution made from the same solvent in a closed system. If we leave this closed apparatus for a while, we will find that the pure solvent is almost completely transferred to the container holding the solution. This occurs because the vapor pressure of the pure solvent is higher than that of the solution. As a result, the molecules of the pure solvent are being trapped by the solution, leading to a net transfer of solvent from the left beaker to the right one. A similar driving force causes the solvent to move from the pure solvent into the solution during osmosis. The osmotic pressure of a solution is directly proportional to the concentration of the solute in the solution, expressed in molarity. It can be calculated using the equation presented on the right, where m is the molarity of the solution, r is the gas constant, and T is the absolute temperature. So, just like boiling point elevation and freezing point depression, osmotic pressure is directly proportional to the concentration of the solution. This is exactly what we would expect, as all colligative properties depend only on the number of solute particles in solution, not on their identity. Two solutions of equal concentration have the same osmotic pressure and are said to be isotonic to each other. We will discuss the implications of osmotic pressure in the following lecture. To sum up, this lecture introduced you to the colligative properties of solutions. We began with an analysis of vapor pressure lowering in solutions, and you learned about Raoult's law, which states that the decrease in vapor pressure is directly proportional to the solute concentration, expressed as a mole fraction. We also discussed boiling point elevation in solutions, noting that it is proportional to the concentration of the solute in the solution, expressed in molality. Similarly, freezing point depression was shown to have many similarities with boiling point elevation and is directly proportional to the concentration of the solute expressed in molality. Finally, you were introduced to osmotic pressure, the pressure required to stop osmosis. We observed that vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure depend only on the number of solute particles present in the solution, not on the nature of the particles. In the following lecture, we will briefly discuss applications of colligative properties. Thank you for your attention.